Nomine Patris et Filii et Spiritus Sancti. Amen. Veni Sancti Spiritus, repletorum corde fidelium et tui moris in eis in accende, imite Spiritum tuum et creabuntur, et renovabiis faciem terrae. Oremus Deus qui corde fidelium Sancti Spiritus illustratione docuisti, da nobis in eodem Spiritu recta sapere, Deus semper consolatione gaudere, per Christum Dominum nostrum. Ave Maria, gratia plena Dominus tecum, benedicta tu in mulieribus, et benedictus fructus ventris tui, Iesus. Santa Maria, Mater Dei, ora pro nobis peccatoribus, nunc et in hora mortis nostrae. Amen. Sede sapientiae, ora pro nobis. Sancti Roberte, ora pro nobis. In nomine Patris, Filii et Spiritus Sancti. Amen. All right, our final lesson of new material for the week is the concept of these special right triangles that pop up a lot in real life and in nature even, and are very important for analyzing more complicated polygons and also for even things like circles, surprisingly enough. When you get into pre-calculus, you'll use these ratios or these ideas quite a bit when talking about something called the unit circle. And so these are actually extremely important in mathematics, and it is definitely something that we needed to have covered before the end of the year. So we did just, in fact, get to it, which is a good thing. So anytime you have a 45, 90 degree triangle, okay, where the three angles in the triangle are those angle measures, it turns out that there's always in for whatever size of triangle that is, they're all going to be similar. Okay, every 45, 90 triangle will be similar to any other because the angles are the same, and that's one of the things we can use to prove similarity, the angle similarity postulate. And in similar triangles, the ratios between the sides is always going to be the same. Okay, there's going to be proportion there. So it turns out that in 45, 90 degree triangles, the ratio is always 1 to 1 to the square root of 2. Okay, and we can prove that this is the case. If we take a 45, 90 triangle and we use the Pythagorean Theorem on this, you'll see that this is the case. So we have three side lengths. If this is 45 and 45 here, that means that this triangle is isosceles, okay, which means that these opposite legs of those 45 degree angles are going to be equal in length. So if A is X, then B is also X. So instead of A and B here, I'm going to go ahead and replace these with, say, X. So whatever the number is, whatever the value this length is, it's going to be the same for both. And if we use the Pythagorean theorem and we set this up, we would say then that x squared plus x squared equals c squared, which means that 2x squared is equal to c squared, which means that when I take the square root here, I have the square root of 2 and the square root of x squared. Well, the square root of something squared is just that variable, and since these are side lengths, I can't have a negative x here, so I don't need to worry about plus minus in this case. It's always going to be the positive value of x. And so we can break the x out of the radical. And we're left with the square root of 2 times x is equal to the hypotenuse. So in other words, whatever length this is for x on either side, this will be in a ratio of 1 to 1. Okay, if I compare x to itself, that's just 1. So that's where the 1 to 1 part of the ratio comes from. Okay, and these are the sides opposite the 45 degree angles. This ratio is 1 to 1, and then the ratio of the hypotenuse to either of these sides is square root of 2 to 1, which is what we have right here. Okay, whatever x is, the hypotenuse is square root of 2 times the length of x. And so this is where we get this ratio, 1 to 1 to the square root of 2. And this is a way of knowing that this is true for all 45, 90 triangles. The 30, 60, 90 triangles are also common and important, but the proof is a little bit more complicated. It's a little bit more difficult, and you kind of have to pull a trick to get this one to work. The ratio in 30, 60, 90 right triangles is 1 to the square root of 3 to 2. And again, what that means is that the So whatever the length of the side opposite the 30-degree angle is, we're going to call that 1. So that's just x, for example. And the side opposite the 60-degree angle will be square root of 3 times that. Okay, but we don't know this yet. We're going to try to prove this. So let's say we have h here for the height of this. And then we have, again, let's just call this c for the hypotenuse. So how do I know that this ratio 1 to root 3 to 2 exists? Well, if I double this 30, 60, 90 triangle and I turn this into an equilateral triangle, I'll have 60 degrees and 60 degrees, which means that 180 minus 60 is going to leave me with another 60 degrees up here, okay, which should make sense because 30 plus 30 is 60. So I have 60, 60, 60 in this larger triangle, which means that this triangle is equilateral. So that means that all the side lengths are equal. So C is equal in length to this side length, x plus x. So C is 2x. So whatever x is, the hypotenuse of that 30, 60, 90 triangle in here is going to be twice x, which is where this number is coming from. Okay, x is just in relation to itself is just 1. X over x is 1. So we have 1 to 2. And now the square root of 3, where does that come from? Again, if I apply the Pythagorean theorem to this, I'm going to get x squared plus h squared equals c squared. But c squared, okay, c is just 2x, remember? So we can substitute that for c, which means that this form of the Pythagorean theorem becomes x squared plus h squared equals 2x squared. And when we square 2x squared, we get 4x squared. And if I subtract the x squared from both sides, then I'm left with h squared equals 3x squared. And when I want to solve for this side length, h, and I take the square root, again, I get this situation where I have an x squared in here, just like I did here, but instead of root 2, I have root 3 as my factor, or as my multiplier of that. So h is going to be root 3 times whatever x is. And so that is the multiplier, or the ratio for that side. So we have 1 to 1 to square root of 3 to 2. Okay, we're going in order of smallest side to largest. So this is the smallest side opposite the 30-degree angle because it's the smallest angle. This is the medium-sized side because it's the middle-sized angle. And the side opposite the 90-degree angle, the hypotenuse, is always the longest. Okay, and if I compare these numbers, root 3 is about 1.73205. Okay, if we convert it to a equivalent decimal, or as close to, I should say, approximate decimal, because we can't actually get perfect equivalence. So it's 1 to 1.7 something to 2. So we get slightly larger as we go around the sides in this ratio. And just for your information, also, you should know that root 2 is about 1.414. Okay, so root 2, less than root 3, but both are in between 1 and 2. Both are less than 2. Okay, so that's the proof. Now, I mean, how do we actually use this, or what is the usefulness of this? Well, if we know that we have one of these types of triangles, we can use this to very quickly, and in fact, in a lot swifter and easier manner than using the Pythagorean theorem or something else, or maybe sine, cosine, and tangent, we can find these other side lengths that we don't know. So if I have, for example, in this triangle, 45, 45, 90, and that's going to be half of a square, basically, okay? That's where this really comes from, in a sense, is if I bisect two of the angles in a square, because it's a rhombus and a square has all 90-degree angles, then this is going to be half of that, which is 45. So you get 45, 45. The side lengths of a square are equal, so there's your isosceles aspect of the triangle, and then the remaining angle is a 90-degree angle. So if I have a triangle like that I know is 45, 45, 90, okay, or maybe they don't even tell me that it's 45 and 45, maybe they just give me 45 and a 90. Well, I can still use what I know about the sum of the angles in here being 180 to deduce that this remaining angle will be 45. So that's often what you'll see is you'll be given only two angles to work with, and you'll have to deduce the third one. But this is in fact going to be 45, 45, 90. And so how do I use this information to find these unknown sides here, x and, well, x, because this is going to be isosceles. Well, just like with other similarity problems and other proportions, we need to multiply by a sort of scale factor, okay, or by the ratio of the relationship between these sides. This is this 1 to 1 to square root of 2. This is sort of like the unit or the smallest or the base triangle for all of these types of similar triangles that are 45, 45, 90. And it just happens to have a side length 1. And in that case, the ratio will be 1 to 1 to the square root of 2. If I increase the size of the triangle or I shrink it and I have a similar one, it won't be necessarily, a side length of 1, but it will be x times 1, okay, in a sense, or it'll be whatever that multiplier is from this unknown side length times 1, and then this side will be that value times square root of 2. So you could set up a little equation here if you like. You could say that, well, I know that 12 is going to be whatever this is, x times the square root of 2, okay, because that's my ratio here. Another way of thinking about this, and this will be more useful when we get to this one, to the 30, 60, 90 triangles, is to take the ratio between the two sides that you're trying to convert between. So I know 12, I know the hypotenuse side, and that corresponds to the root 2, and I'm trying to find this other side x, which is corresponding to 1, let's say. So the ratio there is root 2 to 1. And then depending on which direction I'm going, if I'm going from the smaller side to the larger side, then I multiply by this ratio in this form, okay, which is bigger than 1. Root 2 over 1 is larger than 1, so that's a multiplier. It's going to increase the side, and you're going to get this side length of 12. If I'm going the other way, which is the case here, I know the larger side and I want to find the smaller side, well then again, I need to multiply by something fractional, not by something greater than 1. If I want to shrink this to find what this side is, I need to multiply by this ratio, but in the opposite, or the reciprocal form, I should say. So I multiply by 1 over root 2. Okay, that's another way of thinking about this. So if I took 12 and I multiply by 1 over root 2, I'm going to get 12 over root 2. So that's x. And this is why we just studied and learned again how to deal with these radicals in the denominator. Okay, we don't want this down here, but this is what's going to happen sometimes when you convert from the larger side to the smaller side. You're going to have a root 2, because you're basically dividing. You're going to have a root 2 in the denominator or a root 3 in the denominator or something like that. So the way, again, I simplify this is I multiply by root 2 over 2, which gives me 12 root 2 in the numerator over 2 in the denominator, and then this fraction 12 over 2 will reduce to 6. Okay, so if this hypotenuse in a 45, 45, 90 triangle is 12 units in length, then the other sides will be 6 root 2 units in length. Okay, and that's for both of them because the ratio here is 1 to 1. It means they have to match. Okay, let's try this on a 30, 60, 90 triangle. Okay, the ratios here are different. You have root 3 and 2 and 1 instead of 1 and root 2, but the idea is the same. Okay, here I have the longest side. I have the hypotenuse of this thing is 13. And I want to find x, which is the side across from the 30-degree angle. So that's the side that's going to correspond to 1 in my ratio. So I'm going from the hypotenuse 2 to the side that's 1. So that's the ratio that I'm dealing with is 2 to 1. And I'm going from the larger side to the smaller side. So I'm going to multiply by the reciprocal of that. Okay, I'm going to multiply by the fractional form of this ratio. 13 times 1/2. Okay, so that means that this side length is half of 13, which is 6.5. Okay, and if I wanted to find, let's say now, I wanted to find this other side that corresponds to the 60-degree angle or is opposite it, and it corresponds to the root 3 in the ratio. I could do this in two ways. Now that I know x here is 6.5, the ratio between that is and this side b is 1 to root 3. So if I want to go from smaller to larger, again, this is larger than 1, this is a larger side than this, then I need to multiply it by this ratio. So I could do 6.5 times root 3 over 1, which is just 6.5 times root 3. Okay, or we could think of this as 13 root 3 over 2, because 6.5 was 13 divided by 2. So I could find it that way, or I could go directly from the 13 to that using this ratio between the hypotenuse and that side, which is opposite the 60-degree angle. So let's try that. We're out of space here, so we're going to do this up in the corner. I could take 13 and multiply by either root 3 over 2 or 2 over root 3. And which one do I want to choose? Well, I need to go from a hypotenuse, which is the largest side, to one of the smaller sides. So I need a fractional form of this. Now you might be tempted to see 2 over 3 here and go, oh, that's the fraction, 2/3, or it's something like 2/3. So that's what I'm going to use. That would be a mistake, because remember, root 3 is less than 2. So this is actually the fractional form of this. Root 3 over 2 is about 1.7 over 2. So it's less than, this fraction is less than 1. So that's the one I want to use here to go from the larger side to the smaller side. So I multiply this by root 3 over 2, and I get 13 root 3 over 2, which is exactly what I got doing it the other method by finding this side first and then multiplying by root 3. Okay, I mean, in effect, I'm doing the same thing either way. Okay, so that's really it in theory, and a couple of basic examples there. Let's see how this works in more complex shapes and how we can use this for bigger polygons. We have a regular, well, actually, let's start with these. These are simpler. We have a trapezoid here, and we know that this angle of the trapezoid is 45 degrees. And we want to find, let's say, this height, or we want to find maybe the length of this side of the trapezoid here, x. Well, if I drop this altitude here from this vertex, then I know that that's going to be a 90-degree angle, because that's what altitudes are. They are 90-degree distances which are at 90 degrees from some point. So I have a 45 and a 90, which means that this other angle is going to be 45 also. So I have a 45, 45, 90 triangle hidden, okay, within this trapezoid. And if I break the trapezoid up, I can have this, and then this part of the trapezoid will maybe be a rectangle, okay, or something else. It depends on if these angles are 90 degrees or not, but we're just concerned with this part of it for now. And let's say that I am told that this length here is 5 root 3 or something. Actually, let's make this 5 root 8. So I know that because this is a 45, 45, 90 triangle, that the ratio between this side opposite the 45-degree angle and this x that I'm looking for is going to be 1 to the square root of 2. Okay, and I'm going to the larger side to find x. So x is going to equal this side, 5 root 8, times root 2 over 1. Okay, or just times root 2. You'll get used to this eventually, and you'll be able to skip the over 1 and just realize that you're multiplying by root 2. So we have root 8 times root 2, which is root 16 times 5, which is just 4 times 5, which is 20. Okay, so this length is 5 root 8. The length of this hypotenuse of this triangle, or this side of the trapezoid, will be 20 units long. Okay, and this height, because this is 1 to 1, this ratio between these two is going to be the same as this length. The height here is going to be 5 root 8. Okay, here's a triangle that is split into two triangles, one of which is a 45, 45, 90 triangle on this side on the left, and the other is a 30, 60, 90 triangle on the right. Okay, so again, you have to use a little bit of, not intuition, I would say, but common sense here. If you see that this is 30 and that's all you're given, well, understand that if there's a 90 on this side, this is going to be 90, and then you're left with a 60-degree angle here up at the top. So this triangle in itself is not a 30, 60, 90 or a 45, 45, 90, the larger triangle, but we can divide it into two that are. So again, this is one of the useful aspects of this ratio, or this set of ratios that we can use. So I want to find x and y. But I don't know any of the sides of this 30, 60, 90 triangle. So I have nothing to start my comparison with. I know that the ratio between these is going to be 1 to the square root of 3 to 2, but I don't know what my starting point is. I don't know what my value is for that side length of across from the 30-degree angle. But I do know that in this 45, 45, 90 triangle, I have a hypotenuse which is length 8. So I could use that to find this unknown distance here, z. Okay, so if I multiply 8 times, again, the ratio is root 2 to 1, but I'm going smaller, so I need to multiply by 1 over root 2, or I need to divide by root 2, in other words. So that side length z is going to be 8 over root 2, again, which when I simplify is 8 root 2 over 2, or 4 root 2. That's z. And if that's 4 root 2, and that's the side across from the 30-degree angle, then the side across from the 60-degree angle is going to be root 3 times that. So 4 root 2 times root 3 over 1, which is 4 root 6. Okay, and I cannot simplify root 6 any further. So we're just stuck with that. 4 root 6 is y, and then x is the hypotenuse of this 30, 60, 90 triangle. The ratio between that and this side z is going to be 1 to 2. So this is going to be twice as long as 4 root 2. So x is 8 root 2. Okay, 2 times 4 root 2 will give us 8 root 2. Okay, so in this problem, we've combined both sets of ratios to find what's unknown. Okay, here we have a regular hexagon, A, B, C, D, E, F. And what do we know about regular hexagons? Well, we know that because the sum of all the angles from the formula n minus 2 times 180 is going to be 720. And in a regular polygon, all the angles are the same measure, and there are 6 of them. If I divide that by 6, I know that every one of these interior angles is 120 degrees. Okay, and you might be thinking, well, Mr. Palmer, that is not 30, 60, 90 or 45, 45, 90. No, but if I bisect one of them, then I divide it in 2, and I'll have a 60-degree angle, for example. Okay, and that might be something that we can actually work with. And we also know that the sides of a regular hexagon are all congruent. So we want to find here AD, which is this diagonal across sort of the middle of the hexagon, and then AC, which is its diagonal, which only cuts off a smaller triangular section of it. Let's go ahead and do this smaller one first, because I have a feeling we might need that to analyze AD properly. But this smaller triangle has a 120-degree angle at the top, but then it's isosceles. So if I take 180 minus, 120, I get 60 degrees. And since this is isosceles, then these are going to have to be equal. So that means they're 60, they're what's left divided by 2. So these are 30-degree angles in here. I hope you can see that. So we have 30, 30, and 120. Which is still not 30, 60, 90. But if I were to redraw this, say up here, I were to divide that 120-degree angle with an altitude to this diagonal like that, then I would be cutting it into 60. These angles would be 30, and I could make this altitude, this could be 90. So I want to know this length. This is the base of this triangle here is AC. I need one more piece of information. I need to know the side lengths of this hexagon. So let's say this hexagon has side lengths of 5 centimeters. So if this is 5 centimeters and it's across from the side, it's the hypotenuse, it's across from the 90-degree angle, then that means that this piece here is going to be half of that. Okay, it's the ratio of 2 going back to 1. So we're dividing this by 2. So the height of this thing is half of 5 centimeters, or 2.5. And then the side across from the 60-degree angle is √3 times that. So I can say it's 2.5 √3, or another way of putting that is 5 √3 over 2. And that's half of this diagonal length. Okay, that's this side length of this triangle, but this triangle is identical to it because in a regular hexagon, these side lengths are congruent. So this is also going to be 5 √3 over 2. And if I multiply that by 2, or if I add these two together, then I'm going to get 10 √3 over 2, which is 5 √3. Okay, so AC here is 5 √3. And that gives me a length on this other triangle where I'm looking for AD. So I know now that this length is 5 √3. So we kind of need to maybe redraw this other triangle now. So this is AD, this side, this hypotenuse. This side length is what we just found, 5 √3. This is AC. This side length, DC, is 5 centimeters, again, because this is a regular hexagon, and that's just one of the sides of the hexagon. This angle up here was 30, so out of this 120, that leaves me with 90 here. So that means this is a 90-degree angle. We cut this 120 in half, so that's our 60, and then this was 30, and then this half of this was 60 here, so 60 minus 30 leaves us with 30, or once we know 60 and 90, we know that that's going to be 30 also. So we have 5 centimeters, 5 √3, and AD is the hypotenuse. And the hypotenuse is going to be twice the length of this side across from the 5 centimeters. So AD is just going to be 10 centimeters. And we could also find that, so that's probably the easiest way to find it, but we could also find that by multiplying this side length, 5 √3, by the ratio 2 over √3. The √3s will cancel, and we'll get 5 times 2, which is 10. Okay, so you'll find that in these problems with these special right triangles, there are many different ways oftentimes, or multiple ways that you can approach them. But ultimately, they will all boil down to relying on your understanding and your knowledge of these ratios.